Then buongiorno and welcome to IFOM. Today, as my colleague explained to you, I'm going to show you how we are trying to study mechanical properties and force during tumor formation. Then, in the world now, we can estimate that about every human being will have a cancer, and probably 50% of us may die from it in the next 50 years. Then the problem of cancer is a vast and very important problem for human beings. Then I show you two examples here of cancer. Then on the left is a very common cancer in women. This is the breast cancer, and this is an X-ray of an Indian woman with a large tumor here on the right breast. And this is different example of melanoma, which are a skin cancer related to the fact that if you go to the beach too much and you don't put sunscreen, you end up with this type of mole that grow and develop. Then what are the problems of those structures, here or here? Is that basically they grow in your body, but your body don't see them as something new. They see it as yourself. Then they don't necessarily fight. They don't necessarily try to kill this structure. And this structure grows. As you can see here, there is a very large invasion. Or here you can see those moles where at the edge of those moles, you start to have some protrusive region that start to invade your skin. And they grow. And also they can reach other places. And as pointed by this arrow, you can see this little structure, which originally came from this large mass, and they have grown to the other breast. And that's called metastasis. Then that's the two major problems of cancer. We have hyperproliferation, meaning the structure is getting bigger, and we have metastasis. And this is the tumor that's moving to another place in your body, and growing there, and basically affecting all your functions. How this happens? Then here is a scheme of what's going on here. Then basically, in the breast you have lactation. That's the function of the breast. And there is small structure called secretory acini that produce the milk. And those structures are fine most of your life, but somehow during your life there may be an event where one of these cells that compose this structure will start to proliferate abnormally. What happens? This structure will start to grow. Then you don't feel that. That's the beginning of the story. Then it grows, it starts to push the environment, as you can see here. And at one point, the structure is getting too big, and it will literally explode. And then what happens when you have this explosion? You basically have cells that start to go out of this and start to invade your body. And that's the stage of metastasis. Then hyperproliferation, the mass grows, and metastasis, the cell invade your body in other places. Then how this works? Then hyperproliferation is due to multiplication of cells, called cell division. Metastasis is due to essentially to cell migration, meaning cells that are moving out. Then I show you a couple of examples. This is a movie that I made here in IFOM for Vincenzo Costanzo with these cells. Then this is a video microscopy movie. Then you can see each of these little guys is a cell. And in about 24 hours, you have cells that grow, and you see 9, 12, 13, 14, 15 hours. And what you see, progressively, they invade the entire space available in this experiment. And you have to think that in your body, if you have a nasty cancer, this window of 24 hours is also happening. And the cancer can grow as fast as it is here. Meaning there is some cancer that are fulgurant, that can kill someone in 2-3 months. Then this is the cell division, or hyperproliferation. On the right here, you have one cell that I pick in the field of view here, and you're going to see exactly what I'm talking about. This movie is looping. You have one cell, and at one point, it divides, it makes two cells. And then what happens? You have one cell, two cells, the next step, 4 cells, and then so on. It grows exponentially. That's the hyperproliferation. Then what about the metastasis due to the cell migration? Then I pick another example. Then this example is a group of cells this time. You have those large chunk group of cells. And those cells are compressed in a system that mimic the condition in your breast, for example. And what happens? Then you're going to see how the cell grow over time. Then basically from the central part, here, there is generation of like stream of cell. The cells are migrating out. And that's how a tumor is spreading in your body. Then this is how the tumor gets disseminated. Then, as you know from the title of this talk, we are interested in force. Force meaning a sort of physical sense. Then why force? Then if you think about it in a very simple way, historically, tumors have been identified by the fact that you feel them. Then, to get back to the breast, for example, a woman will touch her breast and then feel something wrong because it feels something hard. And this is because the tumors are changing the physical property of the environment, the mechanical property of the environment. And as such, this is the first step in tumorigenesis. And what happens? Then, for example, when this tumor grows, what you feel is something hard because there is compression. The tumor is growing, it's pushing the environment, and there is a compressive force on it. Then it's a bit like if you have a small T-shirt, when you grow up, if you take when you were 10-year-old your T-shirt, you're not going to be able to feel it. Then that's exactly the same for the tumor. And why it's bad? Let's think about you put this too tight T-shirt. Then you go to a nightclub and stuff, and you feel bad with it. You want to tear it off because it's very uncomfortable. And for the tumor, it's the same. It feels tight. It feels uncomfortable. And biology has this propensity, when it's uncomfortable, it mutates. It changes to make it comfortable. That's the basis of evolution that you find in Darwin when he was looking at the turtles. Then that's compressive force. What do you have also? During metastasis, those cells are getting out. Then you have also cell-based and environmental-based forces that apply for those cells. Then I take those two examples. For the daily life, it's like crawling in a forest or climbing to a tree. Then if you crawl in a forest, then if you are in the center of a city, everything is well laid out, then forests are bare image of what they are, then you have large trees, then it's very easy. Then you don't have to apply much force. But in the body, it's not like that. It's like a very dense Amazonian type of forest. Then you have to push, you have to displace objects. And then if I'm a tiny cell, very weak, I will not go further. But if I'm a very strong cell, then I can push hardly, and then I can invade very fast, then penetrate very fast in your body. And it's a bit also like climbing to a tree, because very often around the cell, you have those sort of fiber-like environment made out of fiber, and the cells are grabbing on it and trying to pull. Then it's a bit like climbing on a tree. Then if you are strong, and you are able to climb very well on a tree, then you are very dangerous, like nasty cell. Then that's the main motor, that's the main idea behind this, is that you have those two major elements, compressive force and mechanical force for the environment of the cell. And we know from times, a very long time, that this force makes nastier cancer, and this force are promoting the bad cell behavior and the bad cell dissemination. Then what are the classic approach to understand cancer? Then unfortunately, what's going on most of the time, you're going to see your doctor. Then the doctor identify something in your body. And generally, in the process that we are describing here, which is the research process, trying to understand what's going on, the doctor will call someone and say, I have this patient with this disease. What's going on and what can you understand of this disease? Then for that, the doctor has a question. And the question will be asked to a scientist, a researcher, mostly biologist. And the biologist will work for years, like 5 years, 10 years, and we'll understand probably the genetic and the biochemistry principle, meaning there is mutation, and there is some elements in your chemistry that doesn't work. And then they can try drugs, first experimentally, and that's the feedback that you get to the doctor. Then you have an answer. I have this, and I have this drug. Let's try. And then if you are winning the game, and that happens unfortunately not so often in cancer, you have a validation, then you have no more cancer. You have a drug that can kill this cancer. Then you have to understand that this process is basically a two-way process, and it takes maybe 20, maybe 30, and some cancer, as you're going to see, it never happened so far. Then that's most of the work that has been done up to 10 years ago, where we start to wonder how we can really measure the force and how we can study those forces that are so nasty. The only way to approach that is by teaming up and by doing a much more interdisciplinary approach. Meaning all of us, we have only one brain. Then you have to understand, to get very good or very specialized in one field of science, like biology or mathematics, you need about 8 years of training. If you want to be interdisciplinary yourself and get a lot of feedback, you're going to need to train for 50 years. Then you're going to die, and you're going to have only train. And that's the major issue. Then the human beings have a limited capacity. Then in order to do that, this is the same approach, but this time the clinician, rather the doctor, than asking the question to only one person, is asking a question to several persons at the same time that work together. And then you have some cell biologists, some people specialize in microscopy, some people in physics, mathematics, bioengineering, physiology, and the list goes on, that team up to understand this cancer. Because I'm a cell biologist by training, and I cannot really shift easily to this mathematics if I want to understand it at a high level. The same way is true, the other way is true. A mathematician will not get what's going on in cell biology. And that's why it's very important to do interdisciplinarity, and that's why also it's very important to practice English, because interdisciplinarity is international. Then if you want to talk to a colleague in the US, a colleague in Japan, a colleague in India, in Singapore, you need a vector, and the vector is the English for the moment. Then we bring an answer, potentially. But how we do that? Then there's 3 major elements to do that. As you have seen, the key point, first to start, is the human capital. The people, you, in maybe 8 years, 10 years, if you like this. You can be a mathematician, a physicist, a medical doctor. Then you will team up with other people in the world or in your city, if it's big enough. And then that's the basis of this interdisciplinarity. And now I'm going to show you a couple of tools and a couple of potential targets that we have identified by this type of approach. Then what are the tools? Then the problem of this field and why it rises recently is because there was not much tool to measure forces at cell and molecular level. You understand it's very, very tiny forces. It's not something that you can approach very easily. Then all that is due, in fact, to a scale issue. Then I put this scheme on the left here to give you a sense of scale. Then what do we know? we know mostly, and we can really understand the human scales. That's what our daily life is about. Then you go from very large structure that we built. For example, this is an aircraft carrier that go up to 200, 300 meters. Then you go down, a house, 20 meters high, a human beings, 2 meters, a bit high here, but anyway, you get the idea. Then, beyond that, we have some idea. Then, this is the liver, for example, it's about the size of, this is Guinea pig. Then we go down, mosquito. Then here we start to have difficulty to see, but this is like little insects. And then, very often, the limit is like something like human hair. This is about the limit that we can feel, touch, see in our scale. But this is like far above what we are talking about when we are talking about cells. Because those guys are composed to multiple cells. This guy is millions of cells. Then we go down. Then we need to go down, and down, and down, and down, and then you start to reach scales like 200 nanometer, 20 nanometer, when you reach the type of scale where you can address your questions. Then what type of force at this scale, what type of capacity those elements here, like a cell or molecule, have, and how we can probe that. That has been the very challenging aspect. Why? Again, some example. This is our classical environment. You have a pack of sugar here, 1 kilogram, a human beings, about 100 kilograms here, and a car, which is about like 1 ton or 1,000 kilograms. Then what are the force here? Then a pack of sugar of 1 kilogram generates about 10 newtons of force. Then that's the force when you lift this back. A human being is 1,000 proportionally, and this car 10,000. It's 1 ton, 1,000 kilogram. That gives you 10,000 newton. Then let's scale this force to this level. Then we start to go down. 1 kilogram, 10 newton. 1 gram, 10 millinewton. 1 milligram, 10 micronewton. We are already like 1 million lighter than this guy, 1 kilogram. We don't even reach yet the cell level. It's only when you start to get at the microgram level, then you get 10 nanonewton, and nanogram level, 10 piconewton, then 1 billion and 1 trillion down, that you reach the level of cell and molecules. Then to give you another example that you may feel, if you take this pack of sugar now, and you take 1 grain, just 1 grain, you barely feel it. You can only feel it if you compress it between your 2 fingers, and then you rub it like that. Then 1 grain of sugar is about 200 microgram in weight, and that's the force that 10 cells combined will apply in average. Then you imagine you need something to measure force applied by cell. You need something very, very sensitive. Then what are the tools? Then I'm going to take a bit of an historical perspective. Then in the 80s, there was this first paper in Science where they tried to measure, this is 1 cell here. Then what do we see here? Then you go to your kitchen, forget about the image first, you go to your kitchen, you have food that's left over, you take a saran noir wrap, you know this plastic wrap, and you put it on top of your food. Very often it's very hard to make it very flat, and there is a wrinkle on it. Wrinkle because you fold it, and if you put your hands on it or stuff, you can create those wrinkles. Then the scientists start to say, okay, then let's try to do the same for a cell scale system. And that's what they did. They made artificial, like, plastic wrap, if you want to see, and they put cell on it, and they look if they were able to literally wrap and wrinkle this. And that's what you have here. This cell is migrating this way, and then you can see this little wrinkle it's applying, meaning it's making forces. Then this was the 80s. Then now, in 2014, like this was a review from my previous colleague, like in Mechano-biology Institute in Singapore. Then we have like those tools, for example, that help us. Then we have different assays. This is a cell in blue that we can use. And I will describe at least 3 of them in details. Then those assays are scaled to the cell and are made to measure force at cell level. Then one of these assays is traction force microscopy. What is traction force microscopy? Then this is a very straightforward and simple concept. Basically, you have a cell that you put now on this substrate, and this substrate is deformable. It's like the wrinkle before, but it's able to be push and pull. It's like a gel, basically, like you take hair gel, for example, to put your hair up, or you take a dessert that is a gel, then you get the idea. It's about the structure here. And people put numerous like beads inside it. Then each bead is embedded in the gel. Then it's not able to move in the gel. Okay? And then if the cell apply some forces on the gel, the beads will move. And you can record the displacement of those beads. Then if they move from the original position to the next position, you can calculate this displacement. And that shows you that the cell is applying forces. Okay? Then how it works. I put you a movie here, made by 2 friends of me, like from France. Then this is again a dividing cell, you're going to see, that is put on this type of substrate. And you're going to see, this has been calculated. The red arrow here, that point inward, are forces applied by the cell on the substrate, calculated from the displacement of those beads. Then this gives me information of the forces implicated in cell division. And I remember you from the beginning of the talk, the cell division is what creates the hyperproliferative phenotype of the cancer, the fact that it grows over and over and over. Then by understanding those basic forces and basic elements, you can start to understand that we can maybe stop this process. The second essay is what I call pillar. Then this is for the ladies here. Then you have this brush that pretty much every girl in his life went through, this type of brush. When you take those brush, what's characteristic if you want to remove your hair is that those pillars are able to move, but they get back to their position. And in order to make them move like that, you apply forces, basically, with your finger. Then this was derived at cell scale, meaning very, very tiny, like pillars, and the cell is laid down on those systems. And then it's pulling. And because we know what is the geometry, we know the properties of those, then we can measure the forces. And that's what I show you here. Then all these red dots are the tip here of one of these guys. This yellow piece here, actually green piece, is a cell. And you're going to see as the cell is a piece of the cell, let's say the back of the cell here, the cell is moving out like that. And you're going to see, oops, sorry. As the cell moves out, you can see it's pulling and relaxing those little structures. It's going to loop back. Then again. Oops, sorry. You can see here the forces. It's pulling, relaxing, pulling, relaxing. Then we can have an accurate view of the forces, and by using different aspects, like in biology tool, we can also look at who's responsible for those forces. For example, here, you have this large, like, green filaments, and you have those little tiny blue dots also, which are molecules, which are the molecule responsible for those forces. Another tool that has been used is a tool that came because of interdisciplinarity. And it's basically using a laser. Then laser, you probably know, like for the show, most of the rockers like Muse here are using those lasers. And I was in a conference like in September when I talked to people, and we were like trying to set up systems. And one of these guys was in fact a roadies from Daft Punk. And this guy was a laser specialist for Daft Punk. And he had the idea to scale down the laser that they use for their show at a level of something compatible for the cell. And for some reason now, you see, it's not because you came from something totally different that you cannot be useful for science. And then they scale up something that is not this system, but another system that I will not talk about, but it's to give you the idea that you really need everybody on board to understand some problems sometime. Then this laser trap is basically using the force that you don't see necessarily, but the force of the light here, of the laser, to hold the objects. Why it's very useful? Because light goes through the cell without affecting it, basically. And you can hold an object and bring it to the cell. Then I will show you an example here that I did. Then that's a work that I did in 2009, where I pull, you see this little bead, I pull a tube, a membrane tube from the cell here. But you can play around. Then this movie is a movie made by my friend in Singapore, Uktur Mizaidov. Then Uktur is from Kazakhstan, and this guy is a physicist. And you can see, for example, he can really like play with those laser trap and trap beads. And he's going to build up a matrix over time. Then he's taking beads one after the other. Then this is held by light. Then the light is holding those objects. And progressively, you can see, he's making this matrix, grabbing one bead after the other, replacing the bead, putting them at the right place. Then now he has the full matrix, and then he can start to move them in concert. Then you can imagine we can really go to the cell and manipulate the cell with this type of system. This, like a system, is scale up for cell and help to manipulate. Then what are the potential targets? Then I show you the human capital required, meaning, for example, there was a physicist doing this laser trap, the guy from Daft Punk doing other stuff. Then we really need like this kind of crazy like ideas to build stuff. And the type of guy we are looking at is, for example, this guy. Then we need a molecule that feels the force. How you feel the force? At your cell, I push this guy. I feel the force because I'm displacing this guy, and it's resisting. Then the cell has some molecules that do the same, and this was identified. For example, there was this molecule called tallinn. When there's no force applied to it, it's about this shape. It's like a long rope, like that. When there's a force applied to it, there is domain that extends, and that helps other molecule, here it's named vinculin, to bind to it. Then, for example, then you have this, you pull it, you expose new domain that can really like bind. Then that's molecular sensor that feel those forces. And that's the kind of target we can develop like chemotherapy after, or elements to avoid this signal, to avoid that the cell is making force on the surrounding environment. But this is not the only forces. In order to apply force, you need sensor, but you need also molecules that do the job, meaning apply the force. One of the best force that we know is our muscle. And then the cell have, similarly, some muscle, which are at the cell's scale, that works in the same principle than our muscle, because we are made of cell, after all. And that's the type of molecule we are looking at. Then I will describe now the strategy that we are trying to apply to one of very nasty cancer in order to get the cues, the molecules that are responsible for the metastatic behavior. Then the cancer that I'm talking about is the glioblastoma. The glioblastoma is a relatively rare cancer, but a very nasty one. It's a rapid killer. Basically, once you are diagnosed, you have like 10 to 14 months of life. And that's about it. And there is, so far, nothing to kill it. There is no cure, and there has been zero progress. Meaning people have proposed, people have tried. The last clinical trial went up, and then they even tried on 600 patients all over the world, but it didn't work at all. There was no progress. Then what's the glioblastoma? Then this is a section of an X-ray in a patient. Then you can see this huge like ball, again, developing in the brain. And this is after death, when you cut the brain, then you get this huge like ball here, and that's what killed the patient. Then it's a proliferation like you have seen from the breast, but in the brain. Then how we approach that? Then from pathologists, people that cut the brain after death and look at it, we know that a lot of cells, the glioblastoma, the cancer cell, they basically go around, they wrap around blood vessel. You can see this yellow coating, like are the cell, around this blood vessel. Then the blood vessel in the brain, there are multiple. There is large blood vessel, but a lot of small capillary that irrigate all over your brain. And that's a scheme representation of it. You have those cells that encase and go. Then we made an animation here for the sake of understanding. Then in red, you have the blood vessel. And in green are your, let me see if it's green, I'm colorblind, then in the other color, this is the cell. And you can see how they migrate along the blood vessel. Then that's their main way of dissemination in your brain. And that's what kills you. This is because progressively, all your brain will get invaded. Then why cell looks, why they look and they like blood vessel? Then blood vessels are numerous, as you see in this animation of the brain. They are all over the brain. They irrigate the brain. And why they like it, the cell? Because it's like a car. You have numerous gas stations, meaning the blood vessel brings what? Food, oxygen. The cell needs that. You need to grow. Then you can have all that from your blood. It's a nice pavement, indeed, around the blood vessel. It's like a very nice highway. You have a smooth ride. It's very clean. And then the cell can grab on it, and they like it. And it's easy to ride because they have space. It's linear. It's very clear of other elements. Then this tree makes this type of motility, this type of metastatic behavior very strong. Then in the mechanobiology and the mechano-oncology approach, we are trying to mimic that to understand what's going on. Then how you mimic blood vessel without having a patient? Then you try to look at how I can make those highway, how I can have straight lines that looks like blood vessel. Then we make like some pattern that's called, that looks like blood vessel. This is all the white, the dark, line here. And then we record cell on it. Then here you have a glioblastoma cell coming from patient. The blue is the nucleus of the cell. And you're going to see how they migrate, how they crawl along this. Then this is a system to imitate what's going on in the brain. And then you can start to study the migration of those cells. Then you team up with mathematicians. And with mathematical tool, you can measure what's going on. Then, for example, here each trace here is a single cell. And this is over time how they migrate. Then you can track each cell, and you can start to see that there is different behavior. For example, those cells, when they're in small capillary-like structure, they go fast and straight. Those cells are more running around. Meaning that when you confine the cell, I remember you at the beginning, I was saying that the more tight you are, the more cell wants to go away. then this is a bit of proof of that. The more tight you are, the less space you have, the more cell is trying to invade and fastly going out. The more space locally you have, the less tight you are, the more in place you stay. Then we can try drugs developed by chemists. Then, for example, in this movie, you have 3 drugs here, and the control, the non-drug cell on the top. They are all on a line, and what's going on? You can see on the top they move, and here they are wound up and they get stuck by the drugs. Some drugs more than others, they are more efficient than others. But globally, we can try with the chemist. They give us a drug, and we say, okay, let's try. And that helps us to have a better understanding of the cancer. Then we can also apply our biological knowledge and make some sort of cell race like you will do with cars, but you do it with cell. Then basically, you put those cells, and you modify each cell to make it less fast or more fast, depending on what you want to study, but generally you want to make it less fast. And you compare that to your control cell. And then, for example, here you have like a couple of cells. Then the control cell is racing along the axis of this line. And different molecules are tested. And you can see that some have no effect almost, then they race. And some totally stop the cell. Then this is our winner. This is our potential target. This is what, after we can feed back to other people, and maybe by developing drug against that molecule, you will kill the capacity of the cell to do metastasis and kill you. It's gonna arrive. I'm starting also to get a bit cooked. Then we can team up with mathematicians. Yeah. Then we can team up with mathematicians and computer scientists. And if you are a very geeky person, you can maybe start to reproduce a pure in silico cell. And this is, for example, the protrusion of a cell, meaning this is this region. You can see here the cell are using this region to move forward, this front of the cell. And then we can make it in silico. And then try to understand, I will not go to the detail, but we really can reproduce. And by testing different scenarios, we can see if the cell is going faster, slower, and if we are rational with our findings. We can go also to clinicians. And that's what we do here. For example, here we have 8 patients, and you can see there is no border. 5 patients are from Italy, IO, the Cancer Institute. And those cells came from Singapore. Then we can try different scenarios and understand what are the common features, what are the less common features of those cells. And finally, I will insist on that because in Italy we have a lot of problems to get animal studies. Then everybody, the politician and a lot of people are like, oh, animal study, let's stop that, it's bad. They don't care. They will kill the cockroach in their kitchen. They will kill all the mosquito. But as soon as you touch mice, they are like, oh no, I like my steak, but not the mice, please. And the problem is that without animal study, we are stuck. We cannot validate our finding. And that you already have to understand it. Because if we don't validate, we go directly to the human beings and we can make huge mistake. And this is, for example, a brain of a mice, where we have reinjected human cells, here in red, and we are trying to see what is the effect of that. And we can team up also with bioengineering. And this is the last slide, almost, where I give you a sort of ultimate tool, ultimate games. Then here we try to build this contraption at cell scale level, where the cell is migrating on the fiber like in the cell body, but we can measure the force by this little pillar I mentioned before. And then that's the type of stuff we have. Then you have a cell here that is pulling on a rope, like a gymnastica type. Then the cell is trying to go on this linear. And you can measure the force by the deflection of the structure on the left that will move in and out. Then, how we do mechano-oncology? By teaming up. And that's really the last word I want to say. this is this notion of interdisciplinarity. Then, for example, to the glioblastoma, I show you that we have biology, physics, chemistry, clinician, bioengineering, computer scientists, mathematical modeling, just to study that. And each of these fields require one brain at least, one person. And this is needed for the future of this field. And with that, I will thank mostly like Pascal here, that works on the glioma, and for sure all those people, and all of you for your kind attention. And I hope you understand something a bit, at least. Thank you very much.